Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Because tonight, I want to tell you about a moment that changed everything we thought we knew about what travels through the darkness between the stars. A moment when the universe itself seemed to reach out and tap us on the shoulder, demanding our attention with a visitor so extraordinary that it would divide the scientific community and force us to confront one of the most unsettling questions imaginable. Are we truly alone? July 1st, 2025. The Atacama Desert of Chile stretches endlessly under a canopy of stars so brilliant they seem close enough to touch. Here, in one of the driest places on Earth, the Atlas Telescope network operates like a cosmic security system, its robotic eyes never blinking, never sleeping, scanning the heavens for anything that dares to move against the fixed backdrop of eternity. At 11:47 p.m. local time, something extraordinary happens. A computer algorithm, processing thousands of images every hour, detects motion, not the lazy drift of a distant asteroid meandering through space, but something moving at 130,000 miles per hour, fast enough to circle our entire planet in just 3 hours, fast enough to escape the gravitational grip of our sun and keep on flying forever into the infinite black. This is the heart-stopping moment when humanity first glimpsed 3I/Atlas, only the third messenger we've ever caught from the vast spaces between the stars. But here's the strange part. This visitor carries secrets that will challenge everything we thought we knew about what travels through the cosmic dark. The discovery unfolds like a detective story, as astronomers around the world begin piecing together a puzzle that stretches back weeks into the past. You see, when they start searching through archived images, looking for earlier glimpses of this mysterious object, they find something that makes their blood run cold. Pre-discovery images. Dating back to June 14th, this visitor from another star system, had been approaching for months, hidden against the bright star fields of the galactic center, invisible to human eyes but captured in digital frames that no one had bothered to examine closely, like a ghost moving through our cosmic neighborhood, leaving traces of its presence that only became clear in hindsight. Each new data point raises more questions than answers. The object appears to be roughly 1 kilometer across, maybe slightly larger, but determining its exact size proves maddeningly difficult because it's simultaneously too far away and moving too fast for traditional measurement techniques. Its surface reflects sunlight with an efficiency that suggests it's covered in something dark, something that absorbs most of the light that hits it and gives back only the faintest glimmer. And then there's the trajectory. When astronomers map its path through our solar system, they discover something that makes their hands tremble as they double-check their calculations. This object isn't just passing through randomly, like cosmic debris thrown into space by some distant catastrophe. No. Its path shows an almost deliberate precision that defies easy explanation. It approaches Venus, it approaches Mars, it approaches Jupiter. The probability of this happening, by pure chance, by the random wandering of an ancient chunk of ice and rock, calculates to less than 0.005%. But what makes the trajectory truly unsettling is how perfectly it aligns with our solar system's ecliptic plane. The flat disk where all the planets orbit the Sunday. It's like a highway designed for optimal access to multiple planetary targets, offering what military strategists would recognize as the perfect approach route for reconnaissance, or something worse. By dawn on July 2nd, one fact becomes undeniably clear. We are witnessing something unprecedented. The international astronomical community erupts into a frenzy of activity. Every major observatory on Earth begins tracking the visitor, and within hours, preliminary spectra start revealing its composition. It's made primarily of ice, the water ice, and something else that will soon prove far more intriguing: carbon dioxide ice, frozen at temperatures so low that it exists in a state of near-perfect preservation, like a time capsule from the birth of another star system. But even as the initial excitement builds, a troubling pattern emerges in the data. This object, this messenger from the void, behaves in ways that stretch the boundaries of conventional comet science. Most comets in our solar system remain dormant until they approach within 2 or 3 astronomical units of the Sunday, roughly the distance of the asteroid belt. The solar heating has to penetrate deep enough into their frozen nuclei to begin the process of sublimation, the transformation of ice directly into vapor that creates the classic glowing coma and streaming tail we associate with these cosmic wanderers. But 3I/Atlas springs to life at 4 astronomical units, still well beyond Jupiter's orbit, beginning to glow and develop that fuzzy envelope of gas and dust, while the Sun remains little more than a bright star in its sky. The reason becomes clear when more detailed spectroscopic analysis reveals the culprit: carbon dioxide ice, the cosmic equivalent of dry ice, which vaporizes at much lower temperatures than water ice. As this alien dry ice begins to sublime in the weak sunlight, it carries with it a cocktail of compounds that paint a picture of formation processes completely foreign to our local cosmic neighborhood. Water vapor streams away at the tremendous rate of 88 pounds per second. Imagine a fire hose running at full blast, but instead of water, it's shooting vapor into the vacuum of space. Mixed within this stellar exhaust, astronomers detect cyanide gas, carbon monoxide, carbonyl sulfide, and even atomic nickel vapor. Elements that speak of stellar environments and chemical processes we've never encountered before. And then there's the anti-tail. Most comets develop tails that point away from the Sun, blown outward by solar wind and radiation pressure like cosmic hair streaming in a stellar breeze. But 3I/Atlas develop something that shouldn't exist: a stream of material pointing directly toward the Sun, defying conventional physics and adding another layer to the growing mystery. What we don't know is even more fascinating than what we do. Where did this object originate? The mathematics of its current trajectory suggest it may have come from the thick disk of our galaxy, a region populated by some of the oldest stars known to exist. Stars that formed when the universe itself was young and wild, when the Milky Way blazed with the violent birth and death of massive suns that forged the heavy elements we see streaming from 3I/Atlas today. How long has it been traveling? Conservative estimates suggest billions of years, possibly as many as 10 billion, meaning this visitor began its journey when our Sun hadn't even formed, and Earth was nothing more than cosmic dust waiting to coalesce. But the question that haunts every astronomer tracking this object, the question that will soon divide the scientific community into warring camps, is simpler and more terrifying. Is this thing natural? Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The discovery of 3I/Atlas represents more than just another astronomical curiosity. It marks the beginning of a new era in humanity's relationship with the cosmos, an era where we possess the technological sophistication to properly investigate interstellar visitors in real time, applying the full arsenal of modern astronomy to decode their deepest secrets. For the first time in human history, we're not just passive observers of the cosmic dance. We're active participants, capable of asking questions that our ancestors could never have imagined, and sophisticated enough to recognize when the answers challenge everything we thought we knew about the universe. The Atlas telescope network that discovered this visitor operates as part of a global early warning system designed to protect Earth from asteroid impacts. Its 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa, scan the entire visible sky every 2 nights, creating a continuous movie of the heavens that captures anything bright enough to pose a potential threat. But 3I/Atlas isn't threatening Earth. Its trajectory will carry it through the inner solar system and back out into interstellar space, never coming closer to our planet than the orbit of Mars. What makes it threatening is something far more subtle. It threatens our assumptions about what kinds of objects travel through the galaxy. As news of the discovery spreads through the astronomical community, observatories around the world begin dropping their regular schedules to focus on this fleeting visitor. The European Southern Observatory's Very Large Telescope in Chile swivels to track the moving target. The twin Keck telescopes in Hawaii coordinate their observations to maximize light-gathering power. Even the aging Hubble Space Telescope, now in its 4th decade of operation, turns its aging but still sharp eye toward this cosmic interloper. Each observation adds another piece to a puzzle that seems to grow more complex rather than simpler with every new data point. The object rotates with a period of 7.6 hours, tumbling end over end as it races through space. Its shape appears to be roughly elongated, possibly cylindrical or cigar-shaped, though the exact geometry remains frustratingly unclear due to the enormous distance and the object's relatively small size. Most intriguingly, its brightness varies dramatically as it rotates, suggesting a surface composition that's far from uniform. Some areas reflect sunlight efficiently, while others seem to swallow it completely, creating a pattern of light and shadow that speaks of complex surface features or composition variations that shouldn't exist on a simple chunk of primordial ice. The more astronomers learn about 3I/Atlas, the more it challenges our understanding of what an interstellar visitor should look like. Natural comets from our own solar system follow predictable patterns of behavior based on 4.5 billion years of observation and theoretical modeling. They heat up gradually as they approach the Sun, develop predictable tail structures, and follow orbital mechanics that conform to our understanding of gravitational physics. But this visitor seems to operate by its own rules. Its early activation at such a great distance from the Sun suggests a composition unlike anything in our local cosmic neighborhood. The presence of carbon dioxide ice in such abundance speaks of formation conditions in a stellar environment, completely different from the one that created our solar system. The exotic chemical cocktail streaming from its nucleus includes compounds that require specific temperature and pressure conditions to form, conditions that point to origins in regions of space we've never directly studied. And lurking beneath all the scientific analysis is a question that no one wants to voice publicly, but everyone is thinking privately. What if the reason 3I/Atlas doesn't behave like a natural comet is because it isn't one? The thought is almost too radical to contemplate. For decades, the search for extraterrestrial intelligence has focused on radio signals from distant stars, looking for patterns in electromagnetic radiation that might indicate the presence of advanced civilizations. The idea that alien technology might actually visit our solar system has been relegated to science fiction and conspiracy theories, dismissed by serious scientists as the realm of UFO enthusiasts and tabloid headlines. But 3I/Atlas forces a different kind of consideration. Here is a genuine interstellar object, confirmed by multiple observatories, exhibiting behavior that challenges conventional explanation. Its trajectory, its composition, its timing, all combine to create a portrait of something that might be more than just cosmic debris from a distant stellar system. The implications are staggering. If even a small percentage of interstellar visitors prove to be artificial rather than natural, it would fundamentally transform our understanding of the galaxy we inhabit. It would suggest that space is not the empty void we imagine, but a bustling highway of objects, some natural, some created by intelligences we've never encountered, traveling between the stars on missions we can barely comprehend. As July turns to August and 3I/Atlas continues its relentless approach toward the inner solar system, one thing becomes crystal clear. We are witnessing the beginning of a cosmic detective story that will challenge everything we thought we knew about our place in the universe. The universe has knocked on our door, and now, for the first time in human history, we're sophisticated enough to answer, even if we're not prepared for what we might hear on the other side. Tomorrow, I'll introduce you to the man who dared to ask the question that most astronomers refuse to voice, and the dangerous answer that may change everything we believe about what travels through the darkness between the stars. In the ivy-covered halls of Harvard University, where scientific reputations are built over decades and destroyed in moments, one man has spent the last 8 years asking a question that makes his colleagues deeply uncomfortable. A question so radical, so potentially career-ending, that most astronomers refuse to even consider it seriously. What if some of these visitors from deep space aren't natural at all? Enter Abraham Avi Loeb, a theoretical astrophysicist whose scientific reputation was built on studying the most exotic phenomena in the universe. Black holes that devour entire star systems, the formation of the first galaxies, the physics of cosmic dawn, when the universe emerged from its dark age and lit up for the first time. For most of his career, Loeb was the epitome of mainstream astronomy, publishing hundreds of peer-reviewed papers, serving as chair of Harvard's astronomy department, advising NASA on everything from space missions to the search for life beyond Earth. But then came October 19th, 2017. On that date, the Pan-STARRS telescope in Hawaii detected something unprecedented. The first confirmed interstellar visitor to our solar system, an object so strange and so unexpected that it forced astronomers to create an entirely new classification. They called it 1/2017 U1, but the world would come to know it by its Hawaiian name, Oumuamua, meaning scout or messenger from afar. Oumuamua was unlike anything astronomers had ever seen. Roughly 400 meters long but only 40 meters wide, it tumbled through space like a cosmic cigar, reflecting sunlight in ways that suggested a surface as reflective as polished metal. Most puzzling of all, as it rounded the sun and began its journey back to interstellar space, Oumuamua accelerated, not in the predictable way that gravity would explain, but as if something was pushing it from behind. The acceleration was subtle but unmistakable. Precise measurements showed the object speeding up by amounts that couldn't be explained by solar gravity alone. Something else was affecting its motion, something that drove it faster and faster away from our Sunday. The astronomical community scrambled for explanations. Perhaps Oumuamua was outgassing, releasing jets of vapor that acted like tiny rocket engines. But detailed observations revealed no coma, no tail, no visible signs of the sublimation that creates such effects in normal comets. Maybe it was being pushed by solar radiation pressure, the gentle but persistent force of sunlight itself. But calculations showed that Oumuamua would need to be incredibly thin, almost like a cosmic sail, for radiation pressure to account for the observed acceleration. Most astronomers settled on increasingly exotic natural explanations. Maybe Oumuamua was made of solid hydrogen, frozen so hard it wouldn't sublime even when heated by our Sunday. Maybe it was a dust bunny, held together by weak forces that allowed it to act like a solar sail while appearing solid. Maybe it was a fragment of a larger object, broken apart by some cosmic catastrophe and possessing properties we'd never encountered before. But Avi Loeb looked at the data and reached a different conclusion. In November 2018, more than a year after Oumuamua had disappeared back into interstellar space, Loeb published a paper that sent shockwaves through the scientific community. Working with his postdoctoral researcher Shmuel Bialy, Loeb proposed that Oumuamua's unusual properties, its extreme shape, its reflective surface, its anomalous acceleration, could be explained if it were artificial rather than natural. Not a chunk of ancient ice and rock from another star system, but a piece of technology, perhaps a solar sail, sent by an alien civilization for purposes we could only guess at. Maybe a probe designed to study star systems like ours, or possibly something even more exotic, the technological remnant of a civilization that had ceased to exist eons before Earth even formed. The reaction was swift and brutal. Loeb found himself branded as everything from a publicity seeker to a pseudo-scientist, accused of abandoning rigorous methodology in favor of sensational speculation. Colleagues who had respected his work for decades suddenly treated him like a pariah. Conference invitations dried up. Peer reviewers became increasingly hostile. The very suggestion that Oumuamua might be artificial was treated not as a legitimate scientific hypothesis to be tested, but as a betrayal of everything astronomy stood for. But Loeb refused to back down. The worst thing that can happen to a scientist, he would later write, is to develop an emotional attachment to a particular outcome. He argued that dismissing the artificial hypothesis without proper investigation was itself unscientific, that extraordinary claims require extraordinary evidence, but they also deserve extraordinary attention. And now, staring at the data streaming in about 3I/Atlas, Loeb sees patterns that make his pulse quicken all over again. This new visitor approaches Venus, Mars, and Jupiter with mathematical precision that defies easy explanation. The probability of such a trajectory occurring by pure chance, by the random wandering of cosmic debris, calculates to less than 0.005%. Those aren't odds that inspire confidence in natural origin. But it's more than just the trajectory that troubles Loeb, it's the timing. 3I/Atlas arrives from a specific region of the galactic coordinates, the same general area of sky that produced the famous WOW signal detected by the Big Ear radio telescope in 1977. That signal, a 72-second burst of radio energy that matched exactly what astronomers expected from an artificial extraterrestrial transmission, remains the most compelling potential alien communication ever recorded. Coincidence? Loeb doesn't believe in cosmic coincidences, especially when they involve interstellar objects exhibiting anomalous behavior. The trajectory of 3I/Atlas aligns almost perfectly with our solar system's ecliptic plane, offering what military strategists would recognize as optimal access routes to multiple planetary targets. It's not approaching randomly, like debris flung into space by some distant stellar catastrophe. It's approaching systematically, like something designed to survey or study our cosmic neighborhood. Most unsettling of all, 3I/Atlas will pass behind the Sun at its closest approach in late October, creating a perfect 24-hour window when no terrestrial telescope can observe it. This solar eclipse provides exactly the cover needed for what aerospace engineers recognize as a reverse solar Oberth maneuver, an ideal braking technique for any spacecraft wanting to slow down and remain in our solar system rather than continue into interstellar space. The timing seems almost too convenient. Any hypothetical alien intelligence wanting to alter course without detection couldn't ask for better circumstances. Loeb assigns 3I/Atlas a 30 to 40% probability of artificial origin, a calculation that makes his Harvard colleagues wince and sends ripples of controversy through the astronomical community all over again. But he defends his analysis with mathematical rigor, pointing to trajectory calculations, probability assessments, and behavioral patterns that strain natural explanations to the breaking point. Science progresses, Loeb argues, by considering all possibilities, not by ruling out inconvenient ones. But there's something darker underlying Loeb's analysis, a reference that chills everyone who understands its implications. He mentions the dark forest theory, popularized in science fiction but grounded in serious considerations of interstellar politics and game theory. The dark forest hypothesis suggests that the universe might be full of advanced civilizations, but they remain hidden because revealing their location invites destruction. In this scenario, Space becomes a cosmic hunting ground, where civilizations eliminate potential threats before they can develop into competitors. First contact isn't a joyous meeting of minds, but a death sentence delivered from the darkness between the stars. If 3I/Atlas represents alien technology, Loeb suggests, it might not be coming in peace. Its trajectory offers perfect access to multiple planetary targets. Its approach from behind the sun provides ideal cover for reconnaissance, or worse. Its timing coincides with humanity's emergence as a technological civilization capable of space travel and interstellar communication. The mathematics are undeniable, but the implications are terrifying. As August turns to September and 3I/Atlas continues its relentless approach toward the inner solar system, Loeb publishes his findings in a series of papers that ignite fierce debate throughout the scientific community. Some colleagues dismiss his work as irresponsible speculation. Others, quietly and privately, admit that his calculations raise troubling questions they'd prefer not to consider. But the data doesn't lie. The trajectory analysis shows approach vectors that maximize access to planetary targets while minimizing detection windows. The timing creates perfect opportunities for course corrections hidden behind solar interference. The chemical composition includes exotic compounds that require formation conditions unlike anything in our local cosmic neighborhood. Most disturbing of all is what happens when Loeb's team runs computer simulations of the approach. Using orbital mechanics software originally developed for NASA mission planning, they model thousands of possible scenarios for how 3I/Atlas might behave during its passage through the inner solar system. In 68% of the simulations that assume natural origin, the object continues on its predicted hyperbolic trajectory, swinging around the sun and departing into interstellar space, never to be seen again. But in 32% of the simulations that allow for artificial origin and intelligent course corrections, 3I/Atlas could use its solar encounter to break into a stable orbit around our sun, becoming a permanent resident of our solar system. The implications are staggering. If even a fraction of Loeb's analysis proves correct, humanity might be witnessing not just the arrival of an interstellar visitor, but the deployment of alien technology in our cosmic backyard. Loeb knows he's risking his reputation once again. The scientific establishment that ostracized him after his Oumuamua hypothesis will react even more strongly to suggestions that 3I/Atlas might represent active alien surveillance, or worse. Funding agencies will question his judgment. Colleagues will distance themselves from his work. Academic journals will scrutinize his papers with unprecedented skepticism. But the mathematical evidence demands serious consideration. We have two choices. Loeb tells anyone willing to listen. We can pretend that anomalous objects like Oumuamua and 3I/Atlas are just unusual but natural phenomena that stretch the boundaries of conventional astronomy. Or we can accept that some of them might be artificial and begin developing the scientific methodologies needed to investigate that possibility rigorously. The choice, he argues, will define humanity's future relationship with the cosmos. Before 3I/Atlas, the search for extraterrestrial intelligence focused on passive detection, listening for radio signals from distant stars, analyzing light from exoplanets for signs of industrial atmospheres, scanning the galaxy for megastructures that might indicate advanced civilizations. The assumption was that first contact would come through electromagnetic communication across interstellar distances. But what if that assumption is wrong? What if advanced civilizations don't broadcast their presence to the galaxy, but instead send physical probes to investigate promising star systems? What if the search for extraterrestrial intelligence shouldn't focus on distant signals, but on visiting objects that might already be here? The questions multiply faster than the answers. If 3I/Atlas proves artificial, how many other interstellar visitors have we missed or misidentified as natural phenomena? The Vera Rubin Observatory, scheduled to begin operations in 2026, will detect roughly one new interstellar object per month. With detection rates increasing exponentially, how many of these visitors might represent alien technology rather than cosmic debris? And if alien probes are already surveying our solar system, what are they looking for? Are they conducting scientific research, like our own missions to other planets? Are they assessing our technological development and potential threat level? Or are they preparing for something more ominous, mapping our defenses, cataloguing our resources, planning for scenarios that science fiction has warned us about for decades? Loeb publishes his analysis knowing that it will generate controversy, but convinced that the alternative, ignoring potential evidence of alien technology because it challenges comfortable assumptions, represents a far greater scientific sin. The universe doesn't care about our preconceptions, he writes in his latest paper. It doesn't adjust its phenomena to match our expectations or conform to our comfort levels. Our job as scientists is to follow the evidence wherever it leads, regardless of how unsettling the destination might be. As October approaches and 3I/Atlas begins its final approach toward perihelion, Loeb's work has catalyzed something unprecedented in the history of astronomy: the development of systematic protocols for investigating potentially artificial interstellar objects. For the first time, humanity possesses both the technological sophistication to detect such visitors and the scientific methodologies to evaluate their possible artificial origin. The infrastructure exists to conduct real-time analysis of trajectory anomalies, chemical composition, structural properties, and behavioral patterns that might distinguish alien technology from natural phenomena. Whether 3I/Atlas proves to be an ancient comet or humanity's first confirmed encounter with alien technology, its arrival has forever changed how we approach the question of our cosmic solitude. The Harvard heretic has asked his dangerous question, and now the universe seems poised to provide an answer that could transform everything we believe about our place in the galaxy. Tomorrow, we'll journey back through deep time to understand how this mysterious visitor, whether natural or artificial, he began an odyssey that spans geological ages and carries within it secrets from an era when the universe itself was young and wild. Picture the universe 10 billion years ago, a cosmos so alien and violent that it would be unrecognizable to modern eyes. Our sun hadn't even formed yet. It wouldn't form for another 5.5 billion years. Earth was nothing more than scattered dust grains drifting through the primordial chaos of an unformed solar system. The Milky Way blazed with the birth and death of massive stars that lived fast, burned bright, and died in cataclysmic explosions that seeded space with the heavy elements needed for rocky planets and, eventually, life itself. Somewhere in that ancient cosmos, in a solar system we'll never identify around a star whose name we'll never know, 3I/Atlas began its existence as ice and rock orbiting an alien sun. But what kind of star system could have given birth to this mysterious visitor? The chemical fingerprints streaming from its nucleus, as it approaches our sun, tell a story of formation processes, completely unlike anything in our local cosmic neighborhood. The exotic compounds detected by spectroscopic analysis, carbon dioxide ice in concentrations unknown in our solar system, cyanide gas, carbonyl sulfide, atomic nickel vapor, speak of stellar environments and chemical processes that push the boundaries of planetary formation theory. The mathematics of stellar evolution suggest that 3I/ATLAS originated around a star significantly different from our own Sunday, perhaps a red giant that swelled to enormous size before casting off its outer layers in spectacular planetary nebulae. Maybe a binary system where two stars danced around each other in an ever-tightening spiral, their gravitational interaction creating temperature and pressure conditions unlike anything in single-star systems. Or possibly something even more exotic, a star that formed from gas clouds enriched by previous generations of stellar death, creating chemical abundances that our solar system has never experienced. The isotope ratios locked within 3I/Atlas's frozen nucleus carry the signature of its birthplace like a cosmic fingerprint. When the James Webb Space Telescope analyzes the light spectrum of its outgassing, it's essentially performing forensic archaeology on a sample from another world, reading the chemical story of stellar nucleosynthesis processes that occurred when the universe was less than a quarter of its current age. But then came the catastrophe that changed everything. Some cosmic disaster of unimaginable violence, hurled this peaceful chunk of ice and rock out of its comfortable orbit and into the void at tremendous speed. The physics of such an ejection event strain the imagination. To accelerate a kilometer-sized object to the incredible velocity of 130,000 miles per hour requires forces that dwarf anything in our everyday experience. Perhaps it was a rogue planet, a world the size of Jupiter or larger, wandering through interstellar space after being ejected from its own star system, that passed close enough to gravitationally disrupt the entire architecture of 3I/Atlas's home system. Computer simulations show that such encounters can scatter smaller objects like cosmic billiard balls, sending them flying into interstellar space at hyperbolic velocities that will carry them between the stars forever. Maybe it was the gravitational chaos of a binary star system, where two massive suns spiraled toward each other in their final death dance. As the stars grew closer, their combined gravitational field would create tidal forces powerful enough to tear apart planetary systems, flinging debris across the galaxy like a cosmic slingshot. Such binary mergers are rare but catastrophic, capable of ejecting material at velocities that can escape not just the star system, but the galaxy itself. Or perhaps it was the death throes of its parent star, a supernova explosion that vaporized the inner planets and blasted the outer ones into interstellar space with the force of 1 billion hydrogen bombs detonating every second for months. The shock waves from such stellar explosions can accelerate material to significant fractions of the speed of light, easily enough to send chunks of former planets on journeys that will last until the heat death of the universe. In a matter of hours or days, gravitational forces beyond imagination transformed 3I/Atlas from a peaceful resident of an alien solar system into an interstellar wanderer, beginning an odyssey that would span geological ages, for billions of years, possibly as many as 10 billion. 3I/Atlas tumbled through the void between the stars, its path bent by the gravity of countless suns, accelerated by close encounters with massive objects, gathering velocity like a cosmic snowball rolling downhill through the curved space-time of the galaxy. Every star it passed added momentum through gravitational assist. Each near miss with a stellar system contributed to its eventual breakneck speed through a process that astronomers call gravitational scattering. Like a pinball bouncing between bumpers, 3I/Atlas ricocheted through the galaxy, its trajectory becoming more and more energetic with each gravitational encounter. The mathematics of such a journey boggle the mind. In 10 billion years, traveling at an average speed of 100,000 miles per hour, 3I/Atlas could have covered a distance of 8.7 trillion miles, roughly 140,000 times the distance from Earth to the Sunday. It could have circumnavigated the entire Milky Way galaxy more than 15 times, visiting regions of space that contained stars unlike anything in our local neighborhood. As the eons passed and galaxies collided and reformed around it, 3I/Atlas continued its silent journey through the cosmic dark. It witnessed the birth and death of countless star systems. It passed through regions where new elements were being forged in stellar cores and distributed through supernova explosions. It drifted through the expanding shock fronts of gamma-ray bursts that sterilized entire sectors of the galaxy. All the while, it carried within its frozen nucleus the chemical signature of its birthplace, a time capsule from an era when the universe itself was young and wild, when the first generation of massive stars was beginning to enrich the cosmos with elements heavier than hydrogen and helium. But here's where the story becomes even more extraordinary. The current trajectory of 3I/Atlas doesn't just tell us where it's going. When astronomers run the orbital mechanics backward, they can trace its path through space to determine roughly where it came from. The mathematics suggest an origin point, the thick disk of our galaxy, a region populated by some of the oldest stars known to exist. These ancient suns formed when the Milky Way was still young and chaotic, before the spiral arms settled into their current elegant configuration. They represent the stellar archaeology of our galaxy's early history, carrying within their spectra the chemical signatures of the universe's first billion years. If 3I/Atlas originated in this region, it could be carrying within its frozen nucleus samples of material from the galaxy's primordial era, isotopes, and compounds that formed under conditions that no longer exist anywhere in the modern cosmos. It's literally a messenger from deep time, bearing chemical evidence of stellar processes that occurred when the universe was fundamentally different from what we see today. But the journey through deep time reveals something even more unsettling. 3I/Atlas arrives at our solar system with a velocity that's perfectly calibrated for gravitational capture. If it were moving much faster, it would sweep through our cosmic neighborhood and disappear back into interstellar space without possibility of deceleration. If it were moving much slower, it wouldn't have enough energy to penetrate deep into our solar system and achieve the close solar approach needed for effective reconnaissance. The velocity is optimal, as if the trajectory has been calculated to provide maximum access to our planetary system while maintaining the option for gravitational braking into a stable orbit. Avi Loeb's analysis suggests that the probability of such an optimal approach velocity occurring by natural processes is extraordinarily small. Random gravitational scattering through the galaxy should produce a distribution of approach speeds, with most interstellar objects either moving too fast for capture or too slow for deep penetration. The fact that 3I/Atlas arrives with precisely the right velocity to explore our system thoroughly raises troubling questions about whether its journey has been entirely natural. The trajectory analysis becomes even more concerning when astronomers model the gravitational influences that shaped 3I/Atlas's path during its final approach to our solar system. The object's course appears to have been fine-tuned by encounters with distant stars, bending its path through a series of gravitational assists that resulted in the precise trajectory needed to visit Venus, Mars, and Jupiter in sequence. Such precision is possible through natural processes, but the probability calculations are sobering. Computer simulations suggest that fewer than 1 in 20,000 randomly ejected interstellar objects would develop a trajectory with such optimal characteristics for planetary reconnaissance. The numbers don't prove artificial origin, but they don't inspire confidence in natural explanations either. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. As 3I/Atlas completes its billion-year journey and enters the final phase of its approach to our Sun, it carries with it more than just ice and rock from another star system. It carries the accumulated history of galactic evolution, the chemical fingerprints of stellar processes that shaped the early universe, and possibly the technological artifacts of civilizations that flourished and vanished before our solar system even existed. The isotope ratios locked within its frozen nucleus tell the story of nucleosynthesis processes in stars that died before our Sun was born. The exotic compounds streaming from its surface as it heats up represent chemistry that occurred under conditions of temperature and pressure unlike anything in our local cosmic environment. The trajectory that brought it here encodes the gravitational history of encounters with stellar systems across vast reaches of space and time. But perhaps most remarkably, 3I/Atlas represents our first opportunity to study interstellar material in real time as it approaches and interacts with our solar environment. Previous interstellar visitors like Oumuamua were discovered only after they had already begun their departure from our system. By the time astronomers realized what they were looking at, the objects were already racing away from the Sun and back into the cosmic void. 3I/Atlas is different. Its discovery in early July, while still 4 astronomical units from the Sun, provides months of observation time as it approaches perihelion. Every day brings new data about its composition, structure, and behavior. Every spectroscopic analysis adds another piece to the puzzle of its origins and nature. The chemical detective work reveals layer upon layer of complexity. The water ice that makes up the bulk of its nucleus formed under conditions of extreme cold, temperatures approaching absolute zero that exist only in the deepest regions of interstellar space or in the outer reaches of planetary systems far from their parent stars. But mixed with this primordial ice are compounds that require much higher temperatures to form, materials that could only have originated in the hot inner regions of a stellar system. This contradiction suggests a violent history, a catastrophic event that mixed materials from different regions of its birth system before ejecting the combined debris into interstellar space. It's as if 3I/Atlas represents a sample collection from an entire alien solar system, compressed into a single object and delivered to our cosmic doorstep after a journey spanning geological ages. The organic compounds detected in its outgassing provide another layer of intrigue. Complex carbon-based molecules that are the building blocks of life as we know it. Amino acid precursors, simple proteins, and even more exotic compounds that require sophisticated chemistry to explain. Whether these represent the natural products of stellar chemistry or something more significant remains an open question that will haunt astrobiologists for years to come. But underneath all the scientific analysis lies a deeper mystery that no amount of spectroscopic data can resolve. If 3I/Atlas is natural, if it represents nothing more than cosmic debris from a distant stellar catastrophe, then its arrival forces us to confront the staggering age and complexity of the galaxy we inhabit. 10 billion years is a time span that human minds struggle to comprehend. It represents more than twice the age of our entire solar system, more than 2,000 times the duration of recorded human history, more than 40 million times longer than our species has existed. During this vast epoch, the galaxy has undergone transformations that dwarf anything in our terrestrial experience. Stars have been born, lived their entire lives, and died in spectacular explosions that enriched the interstellar medium with heavy elements. Stellar systems have formed, evolved, and been destroyed by gravitational encounters, supernova shockwaves, and the chaotic dynamics of galactic evolution. Entire regions of space have been sterilized by gamma-ray bursts and then repopulated by new generations of star formation. Through it all, 3I/Atlas has tumbled silently through the void, a tiny fragment of one destroyed world carrying the chemical memory of its birthplace across distances that span significant fractions of the galaxy itself. It has witnessed cosmic history on scales that make human civilization appear as fleeting as a summer lightning storm. And now, after a journey of unimaginable duration through the depths of space and time, it has arrived at our solar system, just as humanity develops the technological sophistication needed to study it properly. The timing seems almost too remarkable to be purely coincidental, as if the universe has conspired to deliver this messenger from deep time precisely when we're ready to receive its secrets. Whether 3I/Atlas represents natural phenomena or something far more significant, its arrival marks a watershed moment in our species' relationship with the cosmos. For the first time in human history, we're conducting real-time analysis of material that originated in another star system, reading the chemical signatures of stellar processes that occurred when the universe was fundamentally different from what we see today. Tomorrow, we'll dive deep into the chemistry of another world as the James Webb Space Telescope begins its forensic analysis of this visitor from the cosmic depths, decoding molecular signatures that paint a picture of alien environments and formation processes that challenge everything we thought we knew about planetary birth. When the James Webb Space Telescope turns its infrared gaze upon 3I/Atlas, it begins the most sophisticated chemical analysis ever attempted on an interstellar visitor. Like a cosmic forensic laboratory, the telescope breaks down the light streaming from the object into its component wavelengths, creating a spectroscopic fingerprint that reveals the molecular secrets locked within its ancient nucleus. What it discovers challenges everything we thought we knew about planetary formation. The data reveals something extraordinary. Carbon dioxide concentrations unlike anything found naturally in our solar system. Not the trace amounts detected in Earth's atmosphere or the moderate quantities seen in the polar ice caps of Mars, but massive deposits of frozen carbon dioxide that make up a significant fraction of the object's total mass. This isn't just unusual, it's unprecedented. In our solar system, carbon dioxide ice exists only under very specific conditions. On Mars, it forms seasonal polar caps that advance and retreat with the planet's eccentric orbit. In the outer solar system, it appears as minor components in the ice mixtures of distant moons and comets. But nowhere in our cosmic neighborhood do we find the kind of carbon dioxide concentrations that 3I/Atlas carries within its frozen nucleus. The isotope ratios tell an even more remarkable story. Carbon dioxide comes in several varieties depending on which isotopes of carbon and oxygen combine to form the molecule. The specific ratios of these isotopes act like fingerprints, revealing the temperature and pressure conditions under which the ice originally formed. The carbon dioxide streaming from 3I/Atlas shows isotope signatures that require formation temperatures approaching absolute zero. The conditions so cold that they exist only in the deepest regions of interstellar space, or in planetary systems far more distant from their parent stars than Pluto is from our Sunday. But mixed with this ultra-cold ice are compounds that could only have formed under much warmer conditions, suggesting a complex thermal history unlike anything in our local experience. But here's where the mystery deepens dramatically. At 4 astronomical units from our Sunday, still well beyond Jupiter's orbit, where sunlight provides barely 1/16 the heating experienced on Earth, 3I/Atlas suddenly springs to life. It begins to glow with the characteristic fuzzy coma of an active comet, developing the streaming tail and brightening signature that astronomers associate with objects much closer to our star. This early awakening puzzles scientists, because most comets in our solar system wait until they penetrate much deeper into the inner solar system before showing such dramatic activity. Water ice, the primary component of most natural comets, doesn't begin significant sublimation until objects approach within 2 or 3 astronomical units of the Sunday. The heating has to penetrate deep enough into their frozen nuclei to begin the process of transformation from solid ice directly to vapor. But 3I/Atlas activates at twice that distance, beginning its spectacular display while our sun remains little more than a bright star in its sky. The reason becomes clear when detailed spectroscopic analysis reveals the culprit: carbon dioxide ice, the cosmic equivalent of dry ice, which vaporizes at much lower temperatures than water ice. As this alien dry ice begins to sublime in the weak sunlight, it carries with it a cocktail of exotic compounds that paint a picture of formation processes completely foreign to our local cosmic neighborhood. Water vapor streams away from the nucleus at the tremendous rate of 88 pounds per second. Imagine a fire hose running at full blast, but instead of liquid water, it's shooting vapor into the vacuum of space at velocities approaching 1,000 meters per second. The mass loss is so dramatic that 3I/Atlas is literally evaporating before our eyes, losing thousands of tons of material every day as it approaches the Sunday. But it's the exotic chemistry mixed within this stellar exhaust that truly astounds astronomers. cyanide gas. Hydrogen cyanide molecules that are both highly toxic and fundamentally important to the chemistry of life. On Earth, cyanide is associated with industrial processes and biological poisons, but in space, it represents one of the key building blocks from which more complex organic molecules can form. The detection of cyanide in such abundance suggests chemical processes that occurred under conditions unlike anything in our solar system. Carbon monoxide, a simple but revealing molecule that forms when carbon and oxygen combine under specific temperature and pressure conditions. The ratios of carbon monoxide to other carbon-bearing compounds provide clues about the oxidation state of the environment, where 3I/Atlas originally formed, suggesting atmospheric conditions in its birth, a system that were fundamentally different from the reducing environment that characterized the early solar nebula from which our planets condensed. Carbonyl sulfide, a compound that requires sulfur-bearing chemistry to explain. The presence of sulfur compounds in significant quantities points to formation processes in a stellar environment with different elemental abundances than our own, possibly around a star that had been enriched by previous generations of stellar nucleosynthesis. Most intriguing of all is the detection of atomic nickel vapor, individual nickel atoms stripped from larger molecules and streaming away from the nucleus at high velocity. Nickel is a relatively rare element in most cosmic environments, typically locked up in metallic cores of rocky planets or distributed in trace amounts through planetary crusts. Finding it in vapor form suggests that 3I/Atlas contains materials that formed under extreme conditions of temperature and pressure, possibly in the deep interior of a differentiated planetary body that was later shattered by cosmic catastrophe. The chemical cocktail streaming from 3I/Atlas reads like a periodic table of alien world formation. Each molecule tells part of a story about stellar environments, planetary formation processes, and chemical evolution that occurred in a star system with properties unlike anything we've encountered in our local galactic neighborhood. But perhaps the most puzzling discovery is what astronomers call the anti-tail. Most comets develop tails that point away from the sun, blown outward by solar wind and radiation pressure like cosmic hair streaming in a stellar breeze. This behavior is so fundamental to comet physics that it's used to distinguish comets from asteroids and other solar system objects. The tail always points away from the sun because that's the direction the solar wind carries ionized gas and radiation pressure pushes microscopic dust particles. But 3I/Atlas violates this basic principle of comet behavior. In addition to its normal tail streaming away from the sun, it develops something that shouldn't exist according to conventional physics: a stream of material pointing directly toward our star. This anti-tail appears in high-resolution images as a faint but unmistakable spike of material extending from the nucleus in the direction opposite to what comet theory predicts. The anti-tail phenomenon has been observed in a few comets from our own solar system, but always as a temporary effect caused by viewing geometry or unusual particle sizes. In 3I/Atlas, the anti-tail persists for weeks and shows spectroscopic signatures that distinguish it clearly from the normal tail material. Several theories attempt to explain this anomalous behavior. Perhaps the anti-tail consists of unusually large particles that are less affected by radiation pressure and solar wind. Maybe it represents material with different electrical charges that respond to the sun's magnetic field in unexpected ways. Or possibly, it indicates that 3I/Atlas is rotating or tumbling in ways that create asymmetric outgassing patterns. But none of these explanations fully account for the persistence and distinctive chemistry of the anti-tail. It remains one of the most puzzling aspects of an already extraordinary object. The chemical analysis reveals layer upon layer of complexity that challenges our understanding of how planetary systems form and evolve. The presence of so many exotic compounds in a single object suggests that 3I/Atlas represents more than just a chunk of ice and rock from another star system. It's more like a geological sample collection, a mixture of materials from different regions of its birth system that were combined during the catastrophic event that ejected it into interstellar space. The water ice that forms the bulk of its nucleus appears to have originated in the cold outer regions of its parent system, where temperatures were low enough to freeze water, but not cold enough to explain the ultra-cold carbon dioxide signatures. The organic compounds require moderate temperatures and complex chemistry to form, suggesting origins in the warm inner regions where rocky planets might have existed. The metallic components, like nickel vapor, point to material from differentiated planetary bodies with iron-nickel cores similar to the terrestrial planets in our own system. It's as if 3I/Atlas is carrying samples from an entire alien solar system: inner planets, outer ice giants, asteroid belts, and cometary reservoirs, all mixed together and compressed into a single interstellar messenger. The implications are staggering for our understanding of planetary formation and stellar system evolution. If 3I/Atlas is typical of interstellar objects, then space is filled with the debris of countless destroyed planetary systems, each carrying the chemical signatures of worlds that formed under conditions different from our own solar environment. But the chemical analysis also raises deeper questions about the nature of 3I/Atlas itself. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The exotic chemistry streaming from 3I/Atlas includes compounds that are difficult to explain through purely natural processes. Some of the organic molecules detected in its outgassing require sophisticated chemistry to form, multi-step reactions that typically occur only in environments where temperature and pressure can be carefully controlled over extended periods. On Earth, such compounds are associated with biological processes or industrial chemistry. In space, they might form through natural processes in stellar atmospheres or interstellar clouds, but the specific combinations and ratios detected in 3I/Atlas suggest formation pathways that stretch the boundaries of astrochemistry theory. Most puzzling are the metallic compounds that shouldn't exist in a typical comet nucleus. The detection of atomic nickel vapor, along with trace amounts of chromium and iron compounds, suggests that 3I/Atlas contains processed materials, substances that have been heated, compressed, and chemically modified in ways that require more than simple condensation from a stellar nebula. Such processing typically occurs in the interiors of large planetary bodies, where radioactive decay and gravitational compression create the high temperatures and pressures needed for differentiation, the process by which heavy elements sink toward the center, while lighter materials rise toward the surface. The presence of these processed materials in an interstellar object implies that 3I/Atlas contains debris from the breakup of a substantial planetary body, possibly an Earth-sized world that was shattered during the gravitational catastrophe that ejected it from its birth system. The isotope ratios of these metallic compounds provide additional clues about the stellar environment where 3I/Atlas originated. The specific proportions of different isotopes reflect the nucleosynthesis processes that occurred in its parent star, revealing details about stellar mass, age, and evolutionary stage that can be compared to our understanding of galactic chemical evolution. The data suggests formation around a star that was significantly more massive than our Sunday, a star that burned hotter and faster, creating different patterns of element formation and distribution. Such stars have much shorter lifetimes than Sun-like stars, living only a few 100 million years before exhausting their nuclear fuel and ending their lives in spectacular supernova explosions. If 3I/Atlas originated around such a massive star, its journey through interstellar space might have begun not with a gentle gravitational ejection, but with the violent death of its parent star in a supernova that vaporized the inner planets and blasted the outer system debris across the galaxy at tremendous velocities. This scenario would explain both the exotic chemistry and the high velocity of 3I/Atlas. Supernova explosions can accelerate material to significant fractions of the speed of light, easily providing the energy needed to send chunks of former planets on journeys that will last until the end of the universe. The shock waves from such stellar deaths also create the extreme conditions of temperature and pressure needed to forge the exotic compounds now streaming from the nucleus as it approaches our Sunday. But the chemical analysis reveals one more mystery that deepens the intrigue surrounding 3I/ATLAS. Hidden within the spectroscopic data are molecular signatures that don't match any known natural compounds. These unidentified lines in the spectrum appear at wavelengths that correspond to complex molecules with structures that challenge our understanding of cosmic chemistry. They might represent natural compounds that form under exotic conditions not found in our solar system, or they could indicate something more remarkable: artificial materials created through industrial processes. The possibility that 3I/Atlas might contain manufactured compounds raises profound questions about its origin and nature. If some of the materials streaming from its nucleus were created through technological processes rather than natural stellar chemistry, it would provide the first direct evidence of extraterrestrial technology, confirming Avi Loeb's most controversial hypotheses about interstellar visitors. But proving artificial origin from spectroscopic data alone is extraordinarily difficult. The universe is capable of creating complex chemistry through natural processes that often mimic the results of technological manufacturing. Distinguishing between natural and artificial compounds requires detailed analysis of molecular structures, isotope ratios, and formation pathways that push the limits of current analytical techniques. As 3I/Atlas continues its approach toward the inner solar system, every new spectroscopic observation adds another piece to the chemical puzzle. The James Webb Space Telescope conducts observations almost daily, building a comprehensive molecular inventory that reveals the true complexity of this interstellar visitor. The chemical story of 3I/Atlas challenges our assumptions about planetary formation, stellar evolution, and the nature of interstellar space. Whether it represents the natural debris of a destroyed alien world or something more significant, its molecular signatures provide our first detailed look at materials that formed under conditions completely different from those that created our own solar system. Tomorrow, we'll witness the most coordinated astronomical observation campaign in human history, as every major telescope and spacecraft in the solar system drops its regular schedule to focus on this fleeting visitor, and discover what happens when humanity turns its full technological arsenal toward decoding the secrets of an interstellar messenger. The appearance of 3I/Atlas triggers something unprecedented in the history of astronomy, the most coordinated observation campaign ever attempted, as every major telescope and spacecraft in the solar system drops its regular schedule to focus on this fleeting visitor from the depths of interstellar space. From Earth's surface, the massive radio dishes of the Very Large Array in New Mexico swivel toward the approaching object, their 27 antennas working in perfect synchronization to create a single instrument with the resolution of a telescope 22 miles across. The operators know the chances of detecting artificial signals are slim, but the possibility is too important to ignore. For 72 hours straight, they listen across multiple radio frequencies, searching for any pattern in the electromagnetic noise that might indicate technology rather than natural phenomena. The Arecibo Observatory in Puerto Rico, or rather, its replacement systems following the collapse of the famous dish in 2020, joins the coordinated effort, adding its sensitivity to the global radio telescope network. Together, these instruments achieve something remarkable. They can detect a signal as weak as a cell phone transmission from the distance of Jupiter, making them sensitive enough to identify even low-power alien communications if they exist. But the radio telescopes detect only silence. Meanwhile, Optical telescopes around the world engage in a different kind of challenge, tracking a target that moves so fast it appears to jump from one star field to another between successive images. The twin Keck telescopes in Hawaii coordinate their observations to maximize light-gathering power, using adaptive optic systems to counteract atmospheric turbulence and achieve image quality that rivals space-based observations. The technique they employ is called tracking and stacking, following the object's motion across the sky while taking hundreds of individual exposures, then combining all those images to reveal details too faint to see in any single photograph. It's like trying to photograph a bullet in flight while riding on a speeding train, requiring computer control systems that can predict the object's position to within fractions of an arc-second. The European Southern Observatory's Very Large Telescope in Chile achieves something even more remarkable. Using its 4 8-meter mirrors working together as an interferometer, it resolves details on the surface of 3I/Atlas that shouldn't be visible from such an enormous distance. The images reveal a roughly elongated object, possibly cylindrical or cigar-shaped, tumbling end over end as it races through space. But it's the brightness variations that prove most intriguing. As 3I/Atlas rotates with a period of 7.6 hours, its brightness changes dramatically, not just dimming and brightening, but shifting in color and spectral characteristics in ways that suggest a surface composition that's far from uniform. Some areas reflect sunlight efficiently, while others seem to swallow it completely, creating patterns of light and shadow that speak of complex surface features or composition variations. The variations are too regular to be random, too structured to be natural weathering. They suggest either geological processes that create dramatic surface contrasts or something else entirely. High above Earth's atmosphere, space-based telescopes add their unique capabilities to the observation campaign. The Hubble Space Telescope, now in its 4th decade of operation, achieves something that will be remembered as one of its greatest accomplishments: the sharpest image ever captured of an interstellar object. Using a technique called target tracking, Hubble follows 3I/Atlas across the sky with precision that allows it to take long exposures without the blurring that would normally result from the object's rapid motion. The resulting image reveals a teardrop-shaped cocoon of dust and gas streaming away from the nucleus, like cosmic hair flowing in a stellar wind. The detail is extraordinary. Individual jets of material can be seen erupting from specific regions of the nucleus, creating a complex pattern of outgassing that defies simple explanation. Most comets show relatively uniform sublimation across their surface, but 3I/Atlas displays localized activity that suggests either unusual composition variations or active control of the outgassing process. Meanwhile, the James Webb Space Telescope conducts what can only be described as a chemical autopsy, breaking down the light from 3I/Atlas into thousands of individual wavelengths to create the most detailed spectroscopic analysis ever attempted on an interstellar visitor. Each wavelength corresponds to specific molecules and atoms, allowing astronomers to identify not just what elements are present, but how they're combined into compounds and at what temperatures and pressures they formed. The data stream from Webb is overwhelming, terabytes of spectroscopic information that require supercomputers to process and analyze. Hidden within those numbers are the molecular fingerprints of an alien world, chemical signatures that reveal formation processes and stellar environments completely different from our local cosmic neighborhood. But the most extraordinary observations come from an unexpected source: our neighbors in space. On Mars, nearly 200 million kilometers from Earth, the Perseverance rover receives an unprecedented command from Mission Control. Despite being designed for geology and astrobiology, not astronomy, the rover is instructed to turn its cameras skyward and attempt something that has never been tried before: photographing an interstellar visitor from the surface of another planet. The challenge is immense. 3I/Atlas appears as little more than a faint smudge against the star field, 100,000 times dimmer than the faintest objects the rover's cameras were designed to detect. The Martian atmosphere, though thin, still creates enough scattering to wash out extremely faint targets, and the rover's cameras lack the sophisticated tracking systems needed to follow rapidly moving objects across the sky. But the mission team develops an ingenious solution. Using the rover's navigation cameras and a technique called drift scan imaging, they program Perseverance to take hundreds of overlapping images while slowly rotating to follow the object's predicted path. Then, using advanced image processing techniques developed for deep space missions, they stack all those images to reveal details too faint to see individually. Against all odds, it works. The resulting images represent a milestone in human exploration. The first photographs of an interstellar visitor taken from the surface of another world. The quality is poor by terrestrial standards, but the achievement is profound. For the first time in history, we have parallax measurements of an interstellar object, images taken from two different planets that allow precise calculation of distance and trajectory. The European and American orbiters circling Mars join the effort, using their more sophisticated cameras to capture additional images from Martian orbit. Despite 3I/Atlas being far below their normal detection limits, both the ExoMars Trace Gas Orbiter and the Mars Reconnaissance Orbiter successfully photographed the visitor, providing crucial data about its behavior as seen from different vantage points in the solar system. As October arrives, 3I/Atlas passes within 30 million kilometers of Mars, still an enormous distance, but the closest approach any human-made instrument will achieve during its passage through our solar system. The Martian observers provide unprecedented coverage of this phase of the encounter, capturing data that would be impossible to obtain from Earth-based telescopes. But the most anticipated observations lie ahead in the mission timeline. In March 2026, as 3I/Atlas swings past Jupiter after its close encounter with the Sun, NASA's Juno spacecraft will face its greatest challenge. The probe, designed to study Jupiter's atmosphere and magnetic field, will temporarily redirect its instruments toward the departing interstellar visitor for what may be humanity's last close look at this mysterious object. The observation window will be brief, perhaps only a few hours, when Juno's BESS, trajectory, and 3I/Atlas's departure path bring them within useful range of each other. But during that window, Juno will deploy its radio antenna array in a configuration never attempted before, listening across multiple frequencies for any signals that might indicate artificial origin. The sensitivity will be extraordinary. At close range, Juno could detect radio transmissions as weak as a garage door opener, making it capable of identifying even very low-power alien communications if they exist. The spacecraft's position beyond Jupiter's radiation belts will also allow it to listen for signals at frequencies that are blocked by Earth's atmosphere, potentially opening entirely new windows for detecting extraterrestrial technology. The coordination required for this global observation campaign stretches the limits of international cooperation. Telescopes controlled by dozens of different organizations in multiple countries work together with precision timing to maximize coverage of 3I/Atlas throughout its passage. Data sharing agreements allow real-time distribution of observations, ensuring that discoveries made by one observatory can immediately guide the observations of others. The effort represents something unprecedented in scientific history, a coordinated planetary response to a potential first contact scenario. Whether 3I/Atlas proves to be natural or artificial, the infrastructure and protocols developed for its observation will serve as a template for investigating future interstellar visitors. But the observations reveal patterns that deepen rather than resolve the mystery surrounding 3I/Atlas. The radio telescopes detect no artificial signals, but they do observe something unexpected: natural radio emissions from the object that vary in intensity and frequency in ways that don't match typical comet behavior. The emissions appear to be synchronized with the object's rotation period, suggesting either unusual interaction with the solar wind or internal structure that affects how electromagnetic radiation escapes from the nucleus. The optical observations reveal surface features that change over time in ways that can't be explained by simple sublimation of ice. Dark and bright regions appear to migrate across the surface, while the overall shape of the object seems to evolve as it approaches the sunday. Such changes could result from non-uniform outgassing that exposes different subsurface materials, but the patterns are more systematic than random thermal effects would predict. Most puzzling are the infrared observations that reveal temperature distributions across the surface that don't match theoretical models of solar heating. Some regions remain significantly cooler than predicted, while others reach temperatures that seem too high for their distance from the sunday. The thermal patterns suggest either unusual composition or active temperature regulation through mechanisms that natural objects shouldn't possess. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. As the observation campaign continues through September and October, the data reveals 3I/Atlas to be more complex and puzzling than anyone anticipated. Each new observation adds another layer to the mystery, rather than providing definitive answers about its nature and origin. The coordinated observations also reveal something profound about humanity's relationship with the cosmos. For the first time in our species' history, we possess the technological infrastructure to conduct real-time, comprehensive analysis of interstellar visitors. The network of ground-based telescopes, space-based observatories, and interplanetary spacecraft creates an observational capability that spans the entire solar system. This infrastructure represents more than just scientific achievement. It represents our emergence as a truly spacefaring civilization, capable of monitoring and investigating cosmic phenomena on a scale that previous generations could never have imagined. We are no longer passive observers of the universe, but active participants in cosmic exploration. The observation campaign for 3I/Atlas also catalyzes the development of entirely new scientific disciplines. Astroarchaeology, the search for technological artifacts in space, emerges as a legitimate field of study with standardized protocols for distinguishing artificial from natural phenomena. Systematic interstellar object research develops methodologies for rapid response observation and analysis that will be essential as the Vera Rubin Observatory begins detecting one new visitor per month. The implications ripple far beyond astronomy. Government agencies begin developing protocols for potential alien contact scenarios. The military considers the strategic implications of objects that can traverse interstellar distances at high velocity. Space agencies recognize the need for rapid response observation capabilities that can be deployed within hours of new discoveries. The scientific community grapples with questions that were purely theoretical just months earlier. How do you prove that an interstellar object is artificial rather than natural? What observations would constitute definitive evidence of extraterrestrial technology? How should humanity respond if such evidence is obtained? These questions become increasingly urgent as the observation campaign reveals the true complexity of 3I/Atlas. The object defies easy categorization, exhibiting properties that stretch the boundaries of both natural and artificial explanations. Its behavior is too systematic to be entirely random, but too complex to be easily explained by known technological principles. The radio observations, while detecting no artificial signals, reveal electromagnetic properties that don't match conventional comet theory. The natural radio emissions vary with the object's rotation in ways that suggest either unusual internal structure or electromagnetic field configurations that require sophisticated physics to explain. The optical observations capture changes in surface features that occur too rapidly to be explained by simple thermal effects. Bright and dark regions appear to shift position over periods of days rather than months, suggesting either very rapid sublimation of surface materials or active reconfiguration of surface properties. The infrared observations reveal thermal behavior that challenges our understanding of how objects heat up and cool down in the vacuum of space. The temperature distributions suggest either exotic materials with unusual thermal properties or active thermal management through processes that natural objects shouldn't be capable of. As October 29th approaches and 3I/Atlas prepares for its closest encounter with the Sun, the global observation campaign reaches fever pitch. Every available telescope focuses on the approaching object, ready to capture what may be the most spectacular cometary display in human history, or something far more significant. The stage is set for the climactic moment of this cosmic drama, when 3I/Atlas will pass within 1.36 astronomical units of our star and reveal whether it continues on its predicted trajectory or exhibits course corrections that would confirm its artificial nature. Tomorrow, we'll witness that climactic encounter as 3I/Atlas races towards solar fire, approaching the moment when it will either vindicate conventional comet theory or force humanity to confront the reality that we may not be alone in the galaxy. October 29th, 2025 marks the crescendo of this cosmic drama as 3I/Atlas reaches perihelion, its closest approach to our Sunday at precisely 14 hours, 23 minutes, and 47 seconds universal time. This visitor from the depths of interstellar space will pass just 1.36 astronomical units from our star, well inside the orbit of Mars, experiencing solar radiation intense enough to transform it from a relatively quiet wanderer into a blazing beacon of cosmic activity. The approach builds like a symphony of increasing intensity as solar heating penetrates deeper into the nucleus, vaporizing ancient ices that have remained frozen since the formation of its parent star system billions of years ago. Every day brings more dramatic changes as the object races toward its appointment with solar fire, its brightness increasing exponentially as more and more material streams away into space. At one point, 5 astronomical units from the Sunday, roughly the distance of Mars, 3I/Atlas begins producing water vapor at rates that stagger astronomers. The 88 pounds per second detected in early October becomes 120 pounds per second, then 160, then 200 as the solar heating penetrates deeper into the nucleus and reaches previously frozen reservoirs of ice. But it's not just water streaming away into space. The exotic chemistry that first puzzled scientists intensifies dramatically as the object approaches perihelion. Cyanide gas production increases by a factor of 5. Carbon monoxide emissions triple. The mysterious atomic nickel vapor that shouldn't exist in a natural comet becomes so abundant that it creates its own spectral lines in the telescope observations. Telescopes around the world prepare to capture this peak performance when 3I/Atlas will be moving at its maximum velocity of 68 kilometers per second and producing its most spectacular tail display. The coordination required is extraordinary. Tracking stations must update their pointing coordinates every few minutes to follow an object that appears to leap from star to star across the night sky. The Hubble Space Telescope achieves something remarkable during this crucial period: time-lapse photography of an interstellar visitor at perihelion. By taking images every 6 hours and combining them into a movie sequence, Hubble captures the evolution of 3I/Atlas in real time, as it transforms from a relatively dim, fuzzy patch into a blazing comet with a tail stretching millions of kilometers into space. The images reveal structure within the coma and tail that defies conventional explanation. Instead of the relatively smooth, symmetrical appearance expected from uniform sublimation, 3I/Atlas displays a complex pattern of jets, streamers, and density variations that suggest either highly non-uniform surface composition or directed outgassing from specific locations on the nucleus. Most intriguingly, the anti-tail that first appeared when the object was still beyond Jupiter's orbit intensifies dramatically as it approaches the Sunday. This stream of material pointing toward our star becomes clearly visible in amateur telescope observations, creating a distinctive appearance that makes 3I/Atlas one of the most photographed comets in history. The persistence and intensity of the anti-tail phenomenon puzzle even veteran comet researchers. While a few comets from our own solar system have displayed temporary anti-tail features under specific viewing conditions, none have maintained such a prominent sunward stream for so long, or with such distinctive spectroscopic characteristics. Some theoretical models suggest the anti-tail consists of unusually massive particles that are less affected by solar radiation pressure and can actually be drawn toward the Sun by gravitational forces. Others propose that the anti-tail represents electrically charged material interacting with the Sun's magnetic field in ways that haven't been observed before. But none of these explanations fully account for the duration, intensity, and chemical composition of the phenomenon. As October 29th approaches, the observations reveal something that makes Avi Loeb's pulse quicken with both excitement and concern. The trajectory of 3I/Atlas remains precisely on course for what aerospace engineers recognize as an optimal deceleration opportunity. During perihelion, the object will pass directly behind the Sun as viewed from Earth, creating a perfect 24-hour window when no terrestrial telescope can observe it. This solar eclipse provides exactly the cover needed for what orbital mechanics specialists call a reverse solar Oberth maneuver, a technique that uses the Sun's gravitational field to change velocity more efficiently than would be possible in deep space. By firing engines or deploying solar sails at exactly the right moment during closest approach, a spacecraft can achieve dramatic changes in trajectory with minimal energy expenditure. The timing seems almost too convenient to be coincidental. Any hypothetical alien intelligence wanting to alter course without detection couldn't ask for better circumstances. The 24-hour observation blackout provides perfect cover for course corrections that would be immediately obvious to Earth-based telescopes under normal viewing conditions. Loeb's analysis suggests that if 3I/Atlas is artificial and intended to remain in our solar system rather than continue into interstellar space, the perihelion passage offers the ideal opportunity to transition from a hyperbolic escape trajectory to an elliptical orbit that would make it a permanent resident of our cosmic neighborhood. The mathematics are unsettling. Computer simulations show that a velocity change of just 3 kilometers per second during perihelion passage would be sufficient to capture 3I/Atlas into a highly elliptical orbit with a period of several decades. Such a maneuver would be undetectable from Earth during the solar occultation, but would become obvious within days as the object emerged from behind the Sun on a trajectory that no longer matched predictions based on pure gravitational dynamics. But there's something even more troubling about the perihelion timing. As astronomers trace the orbital mechanics backward through time, they discover that the perihelion date of October 29th represents more than just the closest approach to the Sunday. It marks the exact moment when 3I/Atlas will be optimally positioned for gravitational assist towards specific targets within our solar system. If the object continues on its predicted natural trajectory, it will depart the inner solar system and head back into interstellar space on a path that takes it nowhere near any significant astronomical targets. But if it executes a course correction during the solar occultation, the modified trajectory could direct it toward Jupiter for another gravitational assist in March 2026, or towards Saturn for a longer-term approach that would bring it back to the inner solar system in the early 2030s. Even more concerning is the possibility of a trajectory modification that would establish 3I/Atlas in an orbit that brings it back to Earth's vicinity within a few years. The gravitational dynamics are complex, but computer simulations show multiple scenarios where a relatively small course correction during perihelion could establish a trajectory that intersects Earth's orbit on subsequent passes. The implications are staggering. If 3I/Atlas represents reconnaissance technology from an advanced civilization, its perihelion passage might not mark the end of our encounter, but the beginning of a much longer and more intensive investigation of our solar system. As the object races toward its appointment with solar fire, astronomers notice something else that defies conventional comet behavior. The nucleus appears to be maintaining structural integrity despite the enormous stresses of close solar approach. Most comets begin to fragment when they approach within 2 astronomical units of the Sunday. The rapid heating and outgassing create internal pressures that can crack and split even relatively solid nuclei, sometimes resulting in spectacular breakup events that create multiple fragments following slightly different trajectories. But 3I/Atlas shows no signs of structural failure, despite producing outgassing rates that should create tremendous internal stresses. High-resolution images reveal a nucleus that remains intact and relatively unchanged in overall shape, even as it streams material into space at rates approaching the theoretical maximum for gravitational binding. The structural resilience suggests either a composition significantly stronger than typical comet materials or internal reinforcement that wouldn't exist in natural objects. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The days leading up to perihelion passage bring a crescendo of observational activity, as every major telescope on Earth and in space focuses on 3I/Atlas. The European Southern Observatory coordinates a 24-hour monitoring campaign using telescopes in Chile, Hawaii, and the Canary Islands to maintain continuous coverage, as Earth's rotation carries different observatories into optimal viewing positions. The intensity of observation reaches levels normally reserved for potentially hazardous asteroids on collision courses with Earth. But 3I/Atlas poses a different kind of threat, not to our physical safety, but to our understanding of the cosmos and our place within it. Radio telescopes increase their sensitivity to maximum levels, searching for any artificial signals that might be transmitted. During the crucial perihelion passage, the massive dishes of the Very Large Array work in perfect coordination, creating an instrument sensitive enough to detect a cell phone transmission from the outer planets. For 72 consecutive hours, they listen across hundreds of radio frequencies, monitoring for patterns that might indicate technology rather than natural phenomena. The silence remains unbroken, but the natural radio emissions from 3I/Atlas intensify dramatically as it approaches the Sunday. The electromagnetic radiation varies in ways that create almost musical patterns, frequencies that rise and fall in harmonies that seem too structured to be random, too complex to be easily explained by conventional plasma physics. Optical telescopes capture the most spectacular images in the history of comet photography. The tail of 3I/Atlas stretches across 15 degrees of sky, roughly 30 times the diameter of the full moon, creating a celestial display visible to the naked eye from dark locations on Earth. But it's the structure within that tail that astounds astronomers. Instead of the smooth, flowing appearance typical of comet tails, 3I/Atlas displays what can only be described as organized streams of material. Parallel filaments of dust and gas flow away from the nucleus in patterns that suggest either highly organized magnetic field interactions or active guidance of the outflowing material. The anti-tail reaches maximum intensity during the final approach, creating a second stream pointing directly toward the Sun that becomes clearly visible in amateur photographs. The spectroscopic signature of this sunward flow reveals chemistry unlike anything in the normal tail, predominantly metallic compounds and exotic molecules that require specific formation conditions to explain. Most remarkable of all are the high-resolution images from the Hubble Space Telescope that reveal surface features on the nucleus itself. Despite the enormous distance and the object's relatively small size, Hubble's precision tracking allows it to resolve details that shouldn't be visible from Earth orbit. The images show a surface with distinctly non-random patterns, geometric structures that appear too regular to be natural geological features. Some of these surface patterns resemble what aerospace engineers would recognize as thermal control systems, areas of high and low reflectivity arranged in ways that would optimize temperature regulation for a spacecraft operating in the extreme thermal environment of close solar approach. Others suggest what could be interpreted as antenna arrays or communication equipment, though the resolution remains too low for definitive identification. As October 29th arrives and 3I/Atlas begins its passage behind the Sun, the global astronomical community holds its collective breath. For 24 hours, humanity will be blind to whatever might occur during the most critical phase of this cosmic encounter. The last images captured before solar occultation show 3I/Atlas blazing with activity, streaming material into space at rates that approach the theoretical maximum for objects of its size, while somehow maintaining structural integrity that defies conventional understanding of comet behavior. The trajectory predictions are precise. If 3I/Atlas continues on its natural hyperbolic path, it should emerge from behind the Sun on October 30th at coordinates that can be calculated to within arc seconds. Any deviation from this predicted position would indicate course corrections that could only be explained by artificial propulsion. The wait begins. 24 hours of uncertainty during which the most important question in human history might be answered. Is 3I/Atlas a natural visitor from the depths of interstellar space? Or has humanity just witnessed the arrival of technology from a Plati Chi Ri civilization that mastered interstellar travel eons before our species even existed? Radio telescopes around the world maintain their vigil, listening for any signals that might leak around the edge of the Sun during the occultation. Deep space tracking networks update their software to capture the exact moment when 3I/Atlas should emerge from behind our star. Rapid response observation protocols stand ready to immediately analyze whatever emerges from the solar glare. The implications of the next 24 hours stretch far beyond astronomy. If 3I/Atlas proves to be artificial, it will fundamentally transform humanity's relationship with the cosmos. We will no longer be alone in the universe, but members of a galactic community that we are only beginning to understand. If it proves natural, the questions multiply rather than diminish. How many other interstellar visitors have we missed or misidentified? What can we learn from objects that carry within them the chemical signatures of alien star systems? How should we prepare for future encounters that might not be as ambiguous? As the solar occultation begins and 3I/Atlas disappears behind the blazing disk of our Sun, one fact becomes undeniably clear. Whatever emerges from behind that stellar fire will forever change how humanity views its place in the cosmic order. The universe has sent us a messenger from the depths of space and time. Tomorrow, we'll discover whether that message comes from the natural processes of stellar evolution and planetary catastrophe, or from minds that looked up at alien skies and decided to reach across the galaxy to touch another world. The next chapter in this cosmic detective story awaits on the other side of solar fire, where mathematics will meet reality, and humanity will learn whether we are truly alone in the vast darkness between the stars. October 30th, 2025, at 11:42 a.m. Universal Time exactly, 24 hours and 19 minutes after disappearing behind the Sun, 3I/Atlas emerges from solar occultation into the waiting gaze of every telescope on Earth. The coordinates match the predictions exactly, to within the measurement precision of the most sophisticated tracking systems humanity possesses. 3I/Atlas appears precisely where gravitational mechanics predicted it would be if it continued on its natural hyperbolic trajectory. No course corrections, no artificial maneuvers, no evidence of the technological intervention that Avi Loeb and others had considered possible during the 24-hour observation blackout. The relief in astronomical circles is palpable, and so is the disappointment. But as the hours pass and more detailed observations accumulate, the story becomes far more complex than a simple vindication of natural origin. 3 I/ATLAS emerges from its solar encounter fundamentally changed, not in trajectory, but in almost every other observable characteristic. The brightness has increased by a factor of 8, making it easily visible to the naked eye as it races away from the Sun toward the outer solar system. The tail now stretches across 25 degrees of sky, creating one of the most spectacular cometary displays in recorded history. But it's the changes in spectroscopic signature that truly astound astronomers. The exotic chemistry that first puzzled scientists has intensified dramatically during the close solar passage. Compounds that were barely detectable before perihelion now dominate the spectrum. New molecular signatures appear that weren't present in earlier observations. Complex organic molecules that require sophisticated formation processes to explain. Most remarkably, the anti-tail that pointed toward the Sun throughout the approach phase has not only persisted through perihelion, but has developed into something unprecedented in comet observation. The sunward stream now extends for millions of kilometers, creating what appears to be a second, independent tail system, with its own distinct chemistry and dynamics. The persistence of this anti-tail phenomenon after closest solar approach violates every model of comet behavior that astronomers have developed over centuries of observation. Solar radiation pressure and solar wind should have eliminated any sunward-flowing material once the object began its departure from the inner solar system. Yet the anti-tail continues to grow stronger rather than weaker as 3 I/ATLAS races toward interstellar space. The spectroscopic analysis of this anomalous feature reveals chemistry that challenges our understanding of how materials behave in the extreme environment of close solar approach. The anti-tail contains metallic compounds that should have been vaporized completely during perihelion passage, yet they persist in organized streams that maintain coherent structure across enormous distances. Whether 3 I/ATLAS proves to be natural or artificial, its behavior has already forced astronomers to rewrite fundamental theories about comet physics and interstellar object dynamics. The observations challenge assumptions that have guided planetary science for generations, opening new questions about how materials from other star systems might behave when exposed to our solar environment. But the impact of 3 I/ATLAS extends far beyond astronomy. For the first time in human history, we have successfully detected, tracked, and comprehensively studied an interstellar visitor in real time using the full arsenal of modern observational technology. The infrastructure developed for this effort, the coordination protocols, the rapid response observation networks, the analytical methodologies, represents a quantum leap in our capability to investigate cosmic phenomena. This success catalyzes the development of entirely new scientific disciplines. Astroarchaeology emerges as a legitimate field of study with standardized protocols for distinguishing artificial from natural phenomena in space. Systematic interstellar object research develops methodologies that will be essential as the Vera Rubin Observatory begins detecting new visitors monthly. The Vera Rubin Observatory, scheduled to begin operations in 2026, represents the next revolution in interstellar visitor detection. Its 8-meter mirror and 3 billion pixel camera will photograph the entire visible sky every 3 nights, creating a continuous movie of the heavens that will capture objects far fainter than current surveys can detect. Conservative estimates suggest the observatory will discover approximately 1 new interstellar object per month, potentially dozens per year. With detection rates increasing exponentially, humanity will soon have a substantial database of visitors from other star systems, allowing statistical analysis of their properties, origins, and behaviors. Each new discovery will be analyzed using lessons learned from 3I/Atlas. The observation protocols, analytical techniques, and theoretical frameworks developed during this encounter will serve as templates for investigating future visitors, gradually building a comprehensive understanding of what travels through the cosmic dark. The implications ripple far beyond astronomy into every aspect of human civilization. Government agencies around the world are forced to confront scenarios they previously considered purely theoretical. What protocols should govern potential alien contact? How should humanity respond if future interstellar visitors prove unambiguously artificial? Who has the authority to speak for our species if contact scenarios develop beyond pure observation? The military implications are equally profound. Objects capable of traversing interstellar distances at high velocity represent technologies that could revolutionize spacecraft propulsion and navigation. The ability to accelerate to 130,000 miles per hour, to escape the gravitational influence of entire star systems, suggests engineering capabilities that dwarf anything in current human technology. Space agencies recognize the need for rapid response observation capabilities that can be deployed within hours of new discoveries. The infrastructure for tracking 3I/ATLAS required months of preparation and international coordination. Future encounters will demand systems capable of immediate response to targets that might be visible for only weeks or days. NASA announces plans for a dedicated interstellar object intercept mission, a spacecraft designed specifically to rendezvous with incoming visitors and conduct close-range investigation impossible from Earth-based telescopes. The European Space Agency proposes a similar concept focused on sample return from interstellar objects, bringing actual material from other star systems back to Earth for laboratory analysis. These mission concepts represent a fundamental shift in space exploration strategy. Instead of traveling to distant targets, humanity will intercept visitors that come to us, using our solar system as a natural laboratory for studying materials and possibly technologies from across the galaxy. The search for extraterrestrial intelligence undergoes its own transformation in response to 3I/Atlas. Traditional SETI focused on detecting radio signals from distant civilizations, assuming that first contact would occur through electromagnetic communication across interstellar distances. But the arrival of potentially artificial interstellar objects suggests a different paradigm. Advanced civilizations might prefer physical exploration over electromagnetic broadcasting, sending probes to investigate promising star systems rather than revealing their locations through detectable transmissions. This probe SETI approach requires entirely different methodologies and technologies. Instead of listening for artificial signals, astronomers must learn to recognize artificial objects among the natural debris of galactic evolution. The techniques developed for analyzing 3I/Atlas, trajectory analysis, compositional studies, behavioral pattern recognition, become the foundation for a new generation of alien technology detection. The philosophical implications are equally profound. Whether 3I/Atlas proves natural or artificial, its arrival forces humanity to confront the reality that we inhabit a galaxy teeming with objects that originated elsewhere, messengers from distant star systems that carry within them the chemical signatures of alien worlds. If even a small percentage of future interstellar visitors prove to be artificial, it would suggest that space is not the empty void we imagine, but a highway of objects traveling between the stars on missions we can barely comprehend. The galaxy would be revealed as a bustling network of civilizations, some active, some extinct, all connected by the slow but persistent flow of interstellar travelers. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The story of 3I/Atlas connects to an even deeper mystery that adds another layer of intrigue to this already extraordinary tale. The object arrives from the same general region of the galactic coordinates that produced the famous WOW signal detected by the Big Ear radio telescope on August 15, 1977. That signal, a 72-second burst of radio energy at exactly the frequency that hydrogen atoms emit when they flip their electron spin, remains the most compelling potential alien transmission ever recorded. It was precisely the type of signal that SETI researchers had predicted an extraterrestrial civilization might use to announce its presence. Narrow band, powerful, and broadcast at a universal frequency that any technological species would recognize as artificially generated. The signal's intensity suggested a transmission power comparable to the total radio output of human civilization, focused into a narrow beam and directed toward our solar system. Despite decades of searching, the signal has never repeated, and no natural explanation has been found for its characteristics. The coincidence of 3I/Atlas arriving from the same region of sky that produced the WOW signal could be purely random, but the probability calculations are troubling. The chances of two unrelated anomalous events originating from the same galactic coordinates within 50 years of each other calculate to less than 1 in several thousand. Avi Loeb and other researchers suggest the connection might be more than coincidental. If the WOW signal represented an artificial transmission from an extraterrestrial civilization, 3I/Atlas could be a physical follow-up. A probe sent to investigate our solar system after radio telescopes detected signs of technological activity on Earth. The timing supports this interpretation. Radio and television broadcasts from Earth have been propagating into space since the 1930s, creating an expanding sphere of electromagnetic radiation that announces our planet's technological status to anyone with sensitive radio telescopes. By the 1970s, these signals would have reached stars within 50 light-years of Earth, roughly the same region that produced both the WOW signal and 3I/Atlas. If an extraterrestrial civilization detected our radio emissions and responded with the WOW signal in 1977, they would have had nearly 50 years to design, build, and launch a physical probe to investigate our solar system. The arrival time of 3I/Atlas fits perfectly within this scenario, suggesting a coordinated response to the discovery of technological activity around our Sunday. The implications are staggering. If this interpretation proves correct, 3I/Atlas might represent the first confirmed response to human radio emissions, evidence that our broadcasts have been detected by intelligence elsewhere in the galaxy, and that this intelligence has taken active steps to investigate our solar system. But whether the connection between the WOW signal and 3I/Atlas proves real or coincidental, the arrival of this interstellar visitor has already transformed humanity's approach to one of the most profound questions we can ask. Are we alone in the universe? The answer may depend not on what we find in distant galaxies, but on what finds us in our own cosmic neighborhood. As new interstellar visitors arrive monthly in the coming decade, each will be analyzed using the methodologies pioneered during the 3I/Atlas encounter. We will search for artificial signals, unusual trajectories, anomalous compositions, and behavioral patterns that might distinguish alien technology from natural phenomena. The age of interstellar archaeology has begun, transforming us from passive observers into active investigators of the galaxy's deepest mysteries. We no longer simply look outward, hoping to detect signs of extraterrestrial intelligence. We examine the visitors that come to us, recognizing that some of them might be looking back. 3I/Atlas may or may not represent our first encounter with alien technology, but it has undeniably marked the beginning of a new era in human cosmic awareness. We now possess the tools and methodologies needed to recognize artificial interstellar objects if they exist, and the infrastructure to coordinate global responses to potential contact scenarios. The universe has awakened us to possibilities we never seriously considered before. As we watch 3I/Atlas race back toward the interstellar void, growing fainter each night until it disappears once again into the cosmic dark, we know that it won't be the last messenger we receive from the depths of space and time. Somewhere out there, in the vast darkness between the stars, other objects are already on their way. Some carry the natural debris of stellar catastrophes and planetary formation. Others might carry messages, technologies, or even representatives from civilizations that mastered interstellar travel long before our world even existed. We are no longer alone in our cosmic ignorance. We have become active participants in a galaxy-wide conversation that we are only beginning to understand. A conversation conducted not through radio waves across the void, but through physical messengers that travel between the stars carrying secrets from distant worlds. The next visitor is already approaching. The question is no longer whether we will recognize it when it arrives, but whether we are prepared for what it might tell us about our place in the cosmic community. The universe has knocked on our door with 3I/Atlas. Now we must decide how to answer when the next visitor arrives, and what we want to say to whoever might be listening from the darkness between the stars.